Also join. Yes, sir. Yes, sir. ಇಂಟ್ರೊಡಕ್ಷನ್ ಶುರು ಆದ್ಮೇಲೆ ರೆಕಾರ್ಡಿಂಗ್ ಕೊಟ್ಬಿಡಿ.
ಕೊಟ್ಟಿದ್ದೀನಿ ಸರ್.
ಮಾಡು.
ಶುರು ಮಾಡೋಣ ಸರ್.
ಶುರು ಮಾಡೋಣ ಖಂಡಿತ. ಓಕೆ.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಇಂದಿನ ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧ ಯೋಜನೆಯ 50ನೇ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಡಾಕ್ಟರ್ ಪಿ ನಾಗರಾಜ್ ಸರ್ ಅವರನ್ನ ಈ ಒಂದು ವೇದಿಕೆಗೆ ಸ್ವಾಗತಿಸುತ್ತಾ ವೆಲ್ಕಮ್ ಟು ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು.
ಸೊ ಸರ್ ಅವರು ಈಗಾಗಲೇ ಹಲವಾರು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಗಳನ್ನು ಕಳೆದ 2 ಸಾಲುಗಳಿಂದನೂ 2021ರಿಂದನೂ ಕೂಡ ಉಪನ್ಯಾಸ ಕೊಡುತ್ತಾ ಬಂದಿದ್ದಾರೆ ತಮ್ಮೆಲ್ಲರಿಗೂ. ಸೊ ಈ 50ನೇ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಅವರನ್ನು ಮತ್ತೊಮ್ಮೆ ಸ್ವಾಗತಿಸುತ್ತಾ ಹಾಗೂ ಇಂದು ಹಾಜರಾಗಿರುವ ನನ್ನ ಎಲ್ಲಾ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರು, ಟೀಚರ್ಸ್ ಹಾಗೂ ಲೆಕ್ಚರರ್ಸ್ಗೂ ಕೂಡ ಸ್ವಾಗತವನ್ನು ಬಯಸುತ್ತಾ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಪ್ರಾರಂಭ ಮಾಡಲು ಅನುವು ಮಾಡಿಕೊಡಬೇಕು ಅಂತ ನಮ್ಮೆಲ್ಲರಿಗೂ ಕೇಳುತ್ತಾ ಓವರ್ ಟು ಯು ಸರ್.
ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು. ಸೊ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೂ ಶುಭವನ್ನು ಕೋರ್ತಾ ಇದ್ದೀನಿ. ಹಾಗೇನೆ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ನನಗೊಂದು ಅವಕಾಶ ಕೊಟ್ಟಂತ KSTA ಚೇರ್ಮನ್, ಆಮೇಲೆ CEO, ಹಾಗೆ ಅಲ್ಲಿರುವಂಥ ಎಲ್ಲ ಸ್ಟಾಫ್ ಮೆಂಬರ್ಸ್ಗೂ ನನ್ನ ವಂದನೆಗಳನ್ನು ಸಲ್ಲಿಸ್ತಾ ನಾನು ಈ ಒಂದು ಟಾಪಿಕ್ ಏನಿದೆ ಡ್ಯುಯಲ್ ನೇಚರ್ ಆಫ್ ರೇಡಿಯೇಷನ್ ಅಂಡ್ ಮ್ಯಾಟರ್ ಅನ್ನೋದನ್ನ ನಿಮಗೆ ಪಾಠ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ಮೊದಲನೇದಾಗಿ ನಿಮ್ಗೆಲ್ಲ ಈ ಪಾಠ ಆಗಿರ್ಬೋದು ಅಂತ ಅಂದ್ಕೊಳ್ತೀನಿ. ಆಗಿಲ್ದೇ ಇದ್ರೆ ಏನಾದರೂ ಮಧ್ಯ ಡೌಟ್ ಬಂದ್ರೆ ಅಥವಾ ನಿಮ್ಗೆ ಗೊತ್ತಾಗದೇ ಇದ್ರೆ ಖಂಡಿತವಾಗೂ ನೀವು ಕೊನೆಯಲ್ಲಿ ಕೇಳ್ಬೋದು. ಯಾಕೆಂದ್ರೆ ಮಧ್ಯದಲ್ಲಿ ಕೇಳೋದಕ್ಕೆ ಇಲ್ಲಿ ಅವಕಾಶ ಇಲ್ಲ ಅನ್ಸುತ್ತೆ. ಹಾಗಾಗಿ ಮೊದಲು ಕೇಳಿಸ್ಕೊಳ್ಳಿ ನಾನು ಏನು ಹೇಳ್ತಾ ಇದ್ದೀನಿ ಅದನ್ನ. ಆಮೇಲೆ ನಂತರ ನಿಮ್ಗೆ ಏನ್ ಕ್ವಶನ್ ಇದೆ ಖಂಡಿತವಾಗೂ ಕೇಳೋದಕ್ಕೆ ಅವಕಾಶ ಇದೆ, ಆಮೇಲೆ ಕೇಳಿಸ್ಕೊಳ್ಳಿ. ಎಸ್, I will start with this dual nature of radiation and matter. First thing is, what do we mean by radiation? And radiation is the emission or the transmission of energy in the form of waves or particles through space at the speed of light or at the velocity of light. Then whenever an electron is accelerated, it emits energy in the form of radiation. Let us say that I don't know whether you have already studied about the Bohr's theory of hydrogen atom. When atom is ionized, we say that. What do we mean by ionized atom? When electron jumps from the ground state to higher energy state, we say that the atom is ionized. Higher energy state, either we say that ionization or excitation. Ionization means if the electron goes from the given state to infinite state, we say that it is ionization. Or in other words, if the electron goes from the given state to any other higher energy state, we say that it is excitation. Therefore, there is a difference between ionization and excitation. Whatever may be the case, when an electron is jumping from higher energy state to lower energy state, it emits energy in the form of radiation. That is what here I have given, that whenever an electron is accelerated, it emits energy in the form of radiation. And any topic with respect to this, either we talk about the Compton effect, photoelectric effect, black body radiation, whatever it is, we have to basically understand the electromagnetic radiation. In other words, we also call it as electromagnetic spectrum. What are the different parts of the electromagnetic radiation? Gamma rays, X-rays, UV, visible, infrared radiation, microwaves, and radio waves. In radio waves, we have actually three parts. SW means short wave, MW means medium wave, and LW means long wave in the increasing order of wavelength or decreasing order of frequency. And remember that if we go from gamma radiation to radio waves, the wavelength is increasing from 0.001 nanometer to almost 500 to 600 meter, not nanometer, because radio waves are in the range of meter. And frequency, if you take, the frequency of gamma radiation is of the order of 10 raised to 21 to 10 raised to 22, whereas the frequency of the radio waves is of the order of 10 raised to 6, but frequency of visible radiation is in the range of 10 raised to 14 hertz. So this is what in brief about the electromagnetic radiation. And electron emission means, in the case of metals, there are the outermost electrons. In other words, we also say that free electrons. What is the definition of free electron? The electrons which are loosely bound to the nucleus of an atom are called free electrons. And these free electrons are emitted under the influence of either the thermal or photoelectric emission or field emission, or what we also call it as secondary emission. In any case, under the influence of external agency, the electrons will be emitted. And let me also tell you in brief about discharge of electricity through gases. And of course, this method uses of electricity through gases at low pressure. The apparatus consisting of a glass tube with two electrodes fused into the tube at its ends. So if you just think of a glass tube and two electrodes are fused into the inside the glass tube, and it contains a gas at low pressure, it is of the order of 0.001 millimeter of mercury. And when we say pressure, you have to use the formula P is equal to rho GH. You have already studied that formula in the first year PUC class. That is P is equal to rho GH means it is rho, that is 13,600. That is actually the density of mercury. G is acceleration due to gravity 9.8, and H is 0.001 millimeter means it is 0.001 into 10 raised to minus 3. If you multiply all those things, that is what we say that is the actual pressure. So what happens when a high voltage is applied between the electrodes? And you know that when high voltage such as about 10,000 volt is applied, then discharge is taken place. In other words, the gas becomes ionized. And when the gas is ionized, it means what? The electrons get separated from the protons. Because even if you consider a gas is actually made up of atoms and molecules. Atom means, again, protons, neutrons, electrons. And basically here, we discuss about ionization, means the electrons get separated. When once the electron gets separated, naturally the radiation is emitted. So when the positive ions bombard the cathode rays, the beam of electrons are nothing but the cathode rays are produced. And these cathode rays were discovered for the first time by William Crookes in the year 1870. And later on, in the year 1897, J.J. Thomson was the first person to determine experimentally the E by M of an electron, or E by M of the cathode rays. In fact, J.J. Thomson model you will study when you are going to study about the atomic models, that according to J.J. Thomson, the atom is a solid of positive charge in which the negatively charged particles are present. And the dimension of an atom is of the order of 10 raised to minus 10 meter. And because there are equal number of positive and negative charges, the atom is electrically neutral. This is what of course, other things are also there. I am not going to discuss about those things. Anyway, you are going to understand those things when you study about the atomic models. Because later on, we have the Lennard's atomic model, Rutherford atomic model, Bohr atomic model, Sommerfeld atomic model, then vector atomic model, and finally we have what is that standard atomic model that was actually introduced in the year 1964. Anyway, you will be studying those things at the later stage, or I don't know whether you must have already studied. So thermionic emission means, like what I have already mentioned, that emission of electrons under the influence of heat, or in other words, we also call it as thermal emission. And the electrons are emitted from a hot tungsten filament. And this was discovered by Thomas Alva Edison in the year 1883. Again, when I repeat that, when metals are heated, the free electron gets separated from the hot surface. It was Richardson and Dashman derived an equation for thermionic emission, and is given by J is equal to A T square e to the power of minus 5 by kT, where J is actually called the current density, a constant of proportionality, T absolute temperature, K Boltzmann constant, and it is 1.38 into 10 raised to minus 23, you know that, and phi the work function. And now come to photoelectric emission. So metals like sodium, potassium, cesium, these are called alkali metals. When alkali metals are exposed to UV or visible radiation or visible light, electrons are emitted. So the emitted electrons are called the photoelectrons, and this phenomena was observed in the year 1887 by Heinrich Hertz. Anyway, I am going to explain the Hertz experiment. And what do we mean by cold emission? It is the process in which by applying a strong electric field to the metal surfaces, then the electrons from it are emitted even at room temperature, and hence it is called the cold emission. Secondary emission, it is again a beam of electrons with large kinetic energy is directed toward the metal surface, and these electrons are called the primary electrons. And when once the electrons are emitted, and if the energy of the primary electrons are very high, then they transfer some of their energy to the metal surface, which leads to called the secondary emission. And now let us understand the concept of light. It is necessary to understand the nature of light. There were two models to start with. That was in the year, in the 17th century. In the year 1637, Descartes introduced a particle nature, and Huygens introduced the wave nature in the year 1678. Even though Descartes introduced the concept of particle nature of light, to start with. That was in the year 1637 itself. But it was Newton in the year 1672 established this particle nature of light, and that is why we call this as Newton corpuscular theory of light. According to this, the light particles, in other words, called the corpuscles, and these corpuscles, when they are emitted from a luminous body, they travel along a straight line with enormous speed. And one thing which you have to remember according to Newton's corpuscular theory of light is the speed of light is more in denser medium than that of the rarer medium. If you look into our the CET question paper, in 2-3 question papers, the same thing has been given in the CET question paper. That is, according to the question which is given in old CET question paper, according to Newton's corpuscular theory of light, the choices are, according to, I repeat the question, according to Newton's corpuscular theory of light, the speed of light dense is more in denser medium than that of the rarer medium, more in rarer medium than that of the denser medium. It is same in both the rarer and the denser medium. Neither A nor B, like that the choices are given. Remember, if this question is repeated by chance, then remember the what is that concept? According to Newton's corpuscular theory of light, the speed of light is more in denser medium than the rarer medium. And it is only with the Newton corpuscular theory it was suggested like that. And you know, like later on, scientists have compared the corpuscles which are emitted from a luminous body similar to that of the bullets fired from the gun. You know, when the bullets fired, they go along a straight line before they fall to the ground. Like that, even the light particles, when once they are emitted from a luminous body, they travel along a straight line, and that travel along a straight line, in other words, we also call it as the rectilinear propagation of light. And though the corpuscular theory of light was able to explain the phenomenon of reflection, and the simultaneous reflection and refraction phenomena could not be explained based on the Newton's corpuscular theory of light. This is also a question whether the Newton corpuscular theory explained simultaneously the reflection and refraction. So when you look at the sentences, each sentence, each word is very important from the point of view of CET. So the last one, what I have stated here, the simultaneous reflection and refraction. So that itself can be asked as a question. CET ನಲ್ಲಿ ಏನು ಒಂದು ಕ್ವಶನ್ ಕೇಳ್ಬೋದು ಅಂದ್ರೆ, ಅಕಾರ್ಡಿಂಗ್ ಟು ಕಾರ್ಪಸ್ಕ್ಯುಲರ್ ಥಿಯರಿ ಆಫ್ ಲೈಟ್, ದಿ simultaneous reflection and refraction explained, not explained. Only reflection applied, only refraction. That means it could not explain simultaneously both the reflection and refraction of light. That is why each and every word and the sentence are important from the point of view of CET or NEET. And even in the NEET examination also, some questions would be repeated like that. And now coming to wave theory of light. The wave theory of light was actually introduced in the year 1678 by Huygens. He suggested that when once the particles are emitted from a luminous body, they travel in the form of a wave. So for the propagation of the disturbance, what do we mean by a wave? The disturbance created in the medium is called the wave, and for the propagation of the disturbance, a medium is required, and that medium, he assumed that it is ether medium. According to Huygens, the ether medium fills the empty space as well as the material medium, and therefore it is called luminiferous ether or all-pervading medium. Of course, based on this medium, ether medium, that is present everywhere, Huygens' theory, wave theory, was able to explain simultaneous reflection and refraction of light, and making use of this Huygens. And one more thing you have to remember, according to Huygens wave theory of light, the light waves are longitudinal in nature. I was about to tell you that transverse. According to Huygens wave theory of light, the light waves are longitudinal in nature. You know already what longitudinal nature is. According to this, the particles are vibrating in the direction of propagation of energy. It is actually called the longitudinal wave. In other words, if the vibration of the particles and the propagation of energy are perpendicular to each other, then we call it as the transverse wave. But anyway, according to Huygens wave theory, the light waves are longitudinal in nature. Based on this, Thomas Young explained the phenomenon of interference in the year 1800. And anyway, I am not going to explain about the Thomas Young's experiment, or we are again studying that in the physical optics, Young's double slit experiment. Because anyway, we are studying in optics, especially in the interference chapter about Young's double slit experiment. I am not going to tell you in detail about these things. But anyway, Thomas Young made use of the Huygens wave theory, and he also assumed that light waves are longitudinal in nature. But Fresnel explained the phenomenon of diffraction, which you may even call it as diffraction. But in order to understand the polarization, again, same Fresnel suggested that light waves are transverse in nature. So these things, again, you are going to study in the other chapter. So electromagnetic wave theory, I think I have already mentioned about that. What is that electromagnetic wave theory? According to electromagnetic wave theory, it was introduced or established by Maxwell in the year 1864. And according to this electromagnetic wave theory, the electric and the magnetic field vectors are at right angles to each other. So the electromagnetic wave is produced in a direction mutually perpendicular to electric and magnetic field displacements. I repeat, the electromagnetic wave is produced in a direction mutually perpendicular to the electric and the magnetic field vectors. Anyway, you are going to study that electromagnetic waves in electromagnetic chapter, and that's why I am not going to tell you about these things. But from this, in order to understand the photoelectric effect, we should know about Planck's quantum theory as well as this. That's why I am just giving you in brief about this. Actually, Maxwell established these four equations. Either we can write it as divergence E is equal to rho by epsilon naught, or divergence D is equal to rho, because divergence D is equal to rho, that is charge density, and divergence B is equal to 0, curl E is equal to minus del B by del T, and curl B is equal to mu naught J plus epsilon naught del T E by delta T. So based on these four equations, he was able to establish the equation for an electromagnetic wave. And the equation for an electromagnetic wave is C is equal to 1 over square root of mu naught epsilon naught. I hope you are able to see that equation at the end of this page, that is C equals 1 over mu naught epsilon naught, where mu naught is the permeability of free space, which is equal to 4 pi into 10 raised to minus 7 Henry per meter, and epsilon naught is the permittivity of free space. It is equal to 8.854 into 10 raised to minus 12 Farad per meter. In fact, what I told you, that mu naught Henry per meter and epsilon naught is Farad per meter. That Farad per meter, you can also, the dimensional formula for mu naught or epsilon naught may be asked. Suppose the question is the dimensional formula for the mu naught, then you have to make use of the formula like F equals mu naught by 4 pi m1 m2, or you can also write it as p1 p2 by d square, where p1 and p2 are the pole strength and the unit of pole strength is ampere per meter. If you know the unit, you can go for the dimensional formula. And even if you go for the permittivity of free space, because you know the dimensional formula of mu naught, epsilon naught, voltage, and then current density, these are all very important. You have to actually practice what is the dimensional formula and what is the unit of mu naught, epsilon naught, these values. And now coming to, I just tell you only in brief about quantum theory of light. The quantum theory of light was introduced in the year 1900 by Max Planck. And according to this theory, radiation is assumed to be made up of discrete packets or quanta. Energy E is equal to nh nu, where n takes the value 0, 1, 2, 3, etc. And h is the Planck's constant. The value of the Planck's constant, you have to remember, it is 6.6025 into 10 raised to minus 34 joule second. And you have to remember even the dimensional formula for the Planck's constant. In order to show you how we get the Planck's constant, we can make use of this formula. E is equal to h nu. N is after all a number. You don't have to bother about it as far as the dimensional formula or even the unit is concerned. You can only write E is equal to h nu or h is equal to E by nu. E is the energy. You know the dimensional formula for the energy and also for the frequency. This is whatever the constant we have. And remember, h is not a dimensionless constant. It is a dimensional constant. That means it has the unit of joule second. And you have to remember even the unit joule second and even the numerical value of the Planck's constant from the point of view of the CET, NEET, or even JEE. Because you know, there may be a small problem. There, the value of H may not be given. If the value of H is not given, you should be able to make use of it by your memory. So what is that called? Quantum. That quantum has been named as photon. That was actually in the year 1924. By mistake here I have written it as 1926. Anyway, that was named by George Newton Lewis, not Isaac Newton. It is George Newton Lewis. He named it as photon. And suppose I just take an example for establishing E is equal to Hc or H nu. For example, consider a bulb of 40 watt emitting red photon. The wavelength of the red light is approximately 700 nanometer. Remember, the wavelength of the visible radiation is almost from 400 nanometer to 800 nanometer. And sometimes you may even write it as 350 to 750 nanometer. It is only for the simplification purpose here the 700 nanometer is taken. So the energy of the red photon you can write E is equal to h nu. Yeah, this is a simple formula, and this simple problem based on the simple formula, which could be given even in your main examination or even in CET, and that is why I am just explaining a small problem related to both the main examination as well as the CET or NEET or any type of entrance examination. So remember that E is equal to h nu, and you also know the relation between the frequency and the wavelength, because normally we write it as V is equal to F lambda. If you replace V by C, F by nu, lambda as it is, so C is equal to nu lambda, or nu is equal to C by lambda. Therefore, HC by lambda. Depending on the value, numerical value given. Suppose the frequency itself is given. Let us say the frequency is of the order of some, say, 10 raised to 15. I'm just telling you the frequency is of the order of 15. Then what you could do, 6.625 into 10 raised to minus 34 into 10 raised to 15. You get the energy in joule directly. Because here it is given in terms of wavelength, you can write that E is equal to h nu, which is also is equal to hc by lambda. And if you just substitute 6.625, I think in the beginning I have made a mistake, 6.60. It is not 6.60, it is 6.625 into 10 raised to minus 34. And c is the speed of light, which we can even call it as the velocity of light, 3 into 10 raised to 8 over lambda, that is 700 nanometer, means 700 into 10 raised to minus 9. If you simplify that, it comes to be nearly 3 into 10 raised to minus 19 joule. Let us say we want to convert that, rather power. So what is the energy? Energy is obtained of that. Next, further, if you want to go for P, that is the power, that means the same problem is given. You may be asked to find out the energy or the power. That's why all I have given, and even the number of photons. So P is equal to Ne, because anyway hc by lambda is nothing but E. So N is equal to P by E. The power is given. We make use of the power as 40 watt, and energy it is already calculated there, 3 into 10 raised to minus 19. And suppose we simplify this, and it comes to be of the order of 10 raised to 20. That means what would be the number of photons? In fact, instead of simply asking only the energy, the power may be asked, and even the number of photons emitted per second could be asked. Yeah, this problem of course has been asked in our main examination, and also in the case of CET and NEET examination. That is why, in addition to the regular topic, I am also giving you some problems like this. So the number of photons emitted per second. So what is the significance of this? Even though the light travels in the form of waves, we say that in fact we are not able to see the light wave, because you know that wavelength of light is of the order of, if I take the average of 400 to 800, it comes to be about 600 nanometer, which we can also rate it as 6 into 10 raised to minus 7 meter. And suppose you convert that into decimal value, it is like 0.00606. And naturally, we will not be able to see the wavelength. Or on the other hand, if you talk in terms of the frequency is of the order of 10 raised to 14. So not even 50 hertz we are able to see. Imagine that whether we can recognize 10 raised to 14 hertz. And on the other hand, based on the calculation what I have given here, the number of photons emitted per second is of the order of 10 raised to 20 means, and naturally the human eye is not able to see such a big number, and therefore what is that, we don't see by our eyes the discrete nature of radiation, and we see only the continuous nature of light. That's why there could be a question like this: even though the light travels in the form of a wave, it appears to travel along a straight line. Why? There could be a question like that, but the same question can also be given in a different form in CET or NEET or in any entrance examination. So here I have given like corpuscular nature, wave nature, photon nature. In fact, we have corpuscular nature by Newton, wave nature by Huygens, photon nature by Max Planck. And the wave particle duality. Yeah, what is this wave particle duality? In fact, in the year 1924, it was the wave particle duality, or light exhibits both in the form of particle as well as wave, and that was actually given by de Broglie. This is where the name is Debrogie. He showed that duality in nature. That means, for example, if you take an electron, the electron behaves as a particle as well as a wave. That means it has both the particle nature as well as the wave nature. Similarly, the neutron, proton, etc. So these particles we exhibit both the particle nature as well as the wave nature of light. And that is why he introduced the concept of duality in nature. In other words, it is called the wave particle duality. And in this, what he done, or what he has established, lambda is equal to h by b. How did he used Einstein's formula, E is equal to h nu, sorry, Planck's formula, E is equal to h nu. That's what just now I told you. But another formula, Einstein formula, E is equal to mc square. Because for the energy according to Max Planck, E is equal to h nu. And according to Einstein, the energy and mass and energy are mutually interconvertible. Especially when you go to nuclear fusion, you will understand the relation between the energy and the mass. You will also find out in terms of the atomic mass unit, then electron volt, all those things you will be studying there. Anyway, in this context, what according to de Broglie, what de Broglie has suggested, that energy as per the Max Planck E is equal to h nu, and for the Einstein's theory, it is E is equal to mc square. Suppose we use these two, then we get a relation like this, that is lambda is equal to um, yes, lambda is equal to h by p, where h is the Planck's constant and p is the momentum. On the left side, lambda represents the wave nature, and on the right side, p is there, and p represents the particle nature. That is why it is called wave particle duality, or duality in nature. That means light exhibits both as a particle as well as a wave. And coming to now the photoelectric effect. Already I have made a mention in the case of alkali metals such as potassium, rubidium, cesium, sodium, the electrons are emitted from these metallic surfaces even under the influence of the visible light. Whereas in the case of metals like zinc, cadmium, cobalt, etc., the electrons are emitted only under the influence of the high energy radiation such as ultraviolet light. But in principle, the photo emission or the electron emission is taken place in the case of solids, liquids, and even gas. Gas means, anyway, I am going to show the already in the discharge of electricity through gases means when high voltage is applied, the gas becomes ionized, and even air is ionized, which I am going to show you in this Hertz experiment. That means photoelectric effect is possible in all, but especially in the case of alkali metals. In laboratory condition, we use only the alkali metals, rhodium, potassium, for the simple reason that the work function for these alkali metal is very less. It is of the order of 2 electron volt. That is why we use that. So already I have mentioned in the year 1864, Maxwell published his theory of electromagnetic radiation. And in the year 1887, Heinrich Hertz, proved the existence of electromagnetic radiation experimentally. What is that experiment? According to Hertz experiment, The experiment is like this. If you just look at the diagram which is given below, on the right side you can see the photograph of Max Planck. Sorry, Hertz, not Max Planck. Max Planck I have shown in the previous slide. And here, if you just look at, you can see two diagrams I have given, but the diagram which is above, you may not be able to follow it clearly. That is why I have given the other diagram. And you can see that the lower diagram, there are two plates, and those two plates A and B, and those two plates A and B act like a capacitor. And these two plates are connected to two metal spheres. They are called S1, S2. And these two metal spheres, along with that square plates, and these square plates either made of brass or zinc, they are connected to secondary of the induction coil, which is nothing but the something like transformer only. And in the above diagram you can see that, and the left side, that is the primary coil. The primary coil is connected to a DC source battery. Low tension battery is of the order of 6 volt or even less than that. And the other coil, which we call it as the secondary coil. But in this diagram, the below diagram, there is some technical mistake. That means both the primary coil and the secondary coil are of same number of turns. Naturally, both will not have the same number of turns. Please rectify that, in the sense, in a secondary coil the number of turns are more. In fact, the ratio of number of turns between the primary and the secondary may be of the order of 1:100. That means if some 100 tons are there in the primary, some 10,000 tons are there in the secondary. Anyway, the secondary coils are connected to secondary of the terminals of the secondary coil are connected to these metal spheres, and they are in turn connected to the square plates A and B, and these square plates A and B are nothing, act as capacitor. The primary coil is connected to a low tension battery along with a switch. Switch is very important here. That switch may be a tap key, or in other words, it may be a plug key. And further, what happens when once the plug key is on, then the current is passing through the primary. When once the current is passing through the primary, EMF is induced in the secondary. The EMF induced in the secondary is very high. And because of the large induced EMF, and induced EMF means it is the voltage, and that voltage actually ionize the gas in between the metal spheres, what you can see as S1, S2, and in turn the what is that plates, square plates A and B get charged. So when once these charge, and you know that the ionized, what is that? The air is ionized. When once the air is ionized, the electrons are emitted and the radiation is produced, and that radiation is in the form of wave, like what you can see. And when once the discharge is taken place, in fact, during the time of discharge, the voltage produced so large compared to charging. Anyway, the plates act like a capacitor, and the voltage produced is very high. Because of the high voltage, the ionization take place, and this radiation is to be detected. In fact, it was Hertz who made use of a circular ring, what you can see there, and that circular ring is provided with a gap in between, and in that gap again the voltage is produced, and that will be detected. So this is what what you can see. Due to the discharge of the capacitor, I will read that. You can see that due to the discharge of the capacitor, what I have already mentioned, that because of small inductance of the plate and connecting rods, discharge take place. I didn't tell you how discharge take place. That is why I'm reading that sentence, because of small inductance of the plates, because plates we have, and those plates and also the connecting rods have small inductance. Discharge take place in the form of a damped oscillatory current of very high frequency, that is electromagnetic waves. And due to discharge of capacitor, the potential difference between the plates falls and their gap stops conducting. However, the capacitor is charged again to a high potential during the break of the primary of the induction coil, and hence discharge again. So this process of charging and discharging of the capacitor generates trains of electromagnetic waves with electric vector parallel to the gap and magnetic vector at right angles to it. And what is the actually what you can see at the end, the paragraph, that Hertz obtained radiations of wavelength 6 meter and frequency 50 megahertz. So Hertz's discovery is that a metallic surface is capable of emitting electrons when light of very short wavelength. Very short wavelength means it may be ultraviolet radiation or X radiation, gamma radiation. So even though experimentally the electromagnetic wave was produced by Hertz, and it was again established by Hallwachs in the year 1888. He conducted a different experiment using ultraviolet radiation, and he made ultraviolet radiation to fall on a zinc plate which is connected to the gold leaves. What you see in the diagram is nothing but the gold leaves electroscope. So we have the gold leaves there, and when once the ultraviolet radiation is made to fall on the top, which is nothing but the brass disc, then charged particles from the metallic zinc plate exposed to ultraviolet radiation. Then what is that? There are three conditions which you have to remember. When ultraviolet radiation is incident on a neutral zinc plate, the plate becomes positively charged. And further, when ultraviolet light is incident on a negatively charged zinc plate, it lost its charge, because the positive charge is produced, positive and negative becomes neutralized. So when ultraviolet light is incident on positively charged zinc plate, it becomes more positively charged. So he came to the conclusion that only negatively charged particles can be emitted by the surface under the action of UV light. So this is again, it was in support of what was done by Henry Hertz in the year 1897. So in 1887, again, J.J. Thomson, I made a mention about J.J. Thomson atomic model, and he actually discovered the electron. So the discovery of electron by whom? It was J.J. Thomson. In fact, I didn't go for G.P. Thomson, and G.P. Thomson was the son of J.J. Thomson, who explained about the diffraction of electron. Father, in the year 1897, discovered the electron, and the son, G.P. Thomson, actually showed that the electron diffraction. So both father and the son got the Nobel Prize. And let me now come to the experimental study of the photoelectric effect. In fact, the experimental study was done by uh, Leonard. In fact, you will also study about the Leonard atomic model. There is a slight difference between Thomson atomic model and the Leonard's atomic model. Thomson stated that atom is a solid mass of positive charge in which the electrons are positive and negatively charges are embedded. It is a solid mass. But what Leonard suggested, that it's not a solid mass, there are large empty spaces in it. Yeah, that is what you are going to study there. But here I'm only talking about what the experiment was done by him with respect to the photoelectric effect. So you can see in the diagram, maybe to my left, that is what we have the cathode. I should have written that as K. And on the right side, it is anode. Cathode is shown little thicker and anode is shown little thinner. So they are the electrodes, and these two electrodes are actually fused into the glass tube. And the light which is actually coming through, and that window is normally made of quartz. The window separately, I have not shown it. The light is passing through the window. Remember, the window is made of quartz, even though the it is a glass tube. And inside the glass tube, you have two electrodes. One is the cathode, and that cathode is thicker in size. That cathode is connected to negative of the variable supply, and anode is connected to positive through an ammeter. No doubt here I am using that ammeter. Ammeter means it is the either the milliammeter or the microammeter, because the current produced is not in the order of ampere, it will be of the order of milliampere, and that is why better you write it as milliampere. So what happens? You know that there is a large gap between the cathode and the anode. When light is made to fall on the cathode is normally made of alkali metals like potassium, rubidium, or any alkali metal. When once the radiation is incident on the photocathode, the electrons are emitted. And these electrons, when once they are emitted, because it is negatively charged, they will be accelerated, and these electrons run toward the anode plate. So when one of the electrons reach the anode plate, then it constitutes the current. Therefore, we get the photoelectric current. That means, suppose you don't allow the light to fall on the cathode, there will be no, in the sense, electrons may be there, but that electrons will be accumulated near the cathode plate, and there is no chance of the electrons being attracted by the anode. So anode is to be maintained at positive potential, and cathode is at negative potential. In addition, that the electrons are emitted, they will actually move toward the anode plate, and thus we have the photoelectric current. And of course, even though it is an experiment, but what are uh, the properties of this, what we can understand? Yes, the experiment is done by varying, because when once we do the experiment, it doesn't mean that simply doing only with one factor. He varied the intensity of radiation, the frequency of radiation, the potential difference between the plates, nature of the material of the cathode. So potential difference between the plates means potential difference between the cathode and the anode. Because when once the experiment is done, we have to verify with various parameters. First one is, let us say, intensity of radiation. Intensity of radiation means how do we increase the intensity of radiation? The intensity of radiation is nothing but the brightness. The intensity of radiation either we can increase by the distance. That means, let us say the light source is brought closer to the cathode. That is one way of increasing the intensity. Or the other way is using different wattage. Let us say first we use 40 watt, next time we can go for 60 watt or 80 watt. We normally don't get it, 100 watt, like that. That means we keep on increasing the intensity of radiation. This is the way. And coming to frequency of radiation, how to increase the frequency of radiation, I will tell you one by one later. How to increase the frequency of radiation? It is using different colors. For example, even if you just think of the visible radiation, the frequency of blue is higher than the frequency of red. The wavelength of red is more, or let us say of the order of 800 nanometer. Naturally, the frequency is less. And the frequency of Blue is more in the sense the wavelength is of the order of say 400 nanometer. The frequency is high, and as the frequency is high, naturally the energy is more. E is equal to h nu. That's what I have given according to Planck's quantum theory. Then potential difference between the plates means we have to increase the potential, decrease the potential. We have to see that what happens to the photoelectric current when the potential difference between the two plates is increased, or the potential difference between the two. Then suppose we go for a different material. That is what we call it as the nature of the material of the cathode. That means instead of using potassium, say we use rubidium, cesium. In addition to that, we can also go for like zinc, cadmium, etc. That means what happens to the photoelectric current if we use different materials. This is what, let me just have a look at it, because he has already given the time. And maybe there are, so photoelectric effect, based on the experimental um, discovery, photoelectric emission is an instantaneous process. It is very important from the point of view of the CET as well as in the main examination. And there may be a question like what are the factors or what are the parameters like that. Under that, photoelectric emission is an instantaneous process. This is based on the experiment. In fact, quantum theory explained this. And according to electromagnetic theory, we have a different explanation. Anyway, it is of the order of 10 raised to minus 9 second. Threshold frequency for a given METI emitter, there is a definite minimum frequency, that is nu naught, called the threshold frequency. There may be a question like, what do we mean by a threshold frequency? So that is the frequency, minimum frequency with which the photoelectric effect takes place. Below this threshold frequency, no photoelectric emission takes place. Or if you multiply that with H, then we call it as the threshold energy. Either we call it as the threshold frequency or threshold energy. Threshold frequency, no doubt it is expressed in terms of hertz, because it is the frequency. If you multiply by H, that is Planck's constant, then we call it as the energy, which is actually measured in terms of electron volt rather than joule. And you should also remember the relation between the electron volt and joule. And remember, 1 electron volt equals 1.6 into 10 raised to minus 19 joule. So threshold frequency is different for different emitter or different material. For incident frequency greater than the threshold, the kinetic energy of the photoelectrons varies directly. That means with increase in frequency, the kinetic energy of the photoelectron increases. Kinetic energy means half mv square. That means with increase in frequency, the velocity of the photoelectron increases, and therefore kinetic energy increases. This is what you can see. That means with increase in energy, or rather the frequency, the kinetic energy increases. Effect of intensity of light on photocurrent means if we increase the intensity, then the magnitude of the photoelectric current increases, but the kinetic energy will not be altered. It is only the magnitude of the photoelectric current, because the number of electrons emitted depends on the intensity of the incident radiation, and that is why here accelerating potential fixed, the intensity of light is varied. So photoelectric current increases linearly with intensity of the incident light, provided the frequency is greater than the threshold frequency, or the photocurrent is directly proportional to the number of photoelectrons emitted. So effect of potential on photoelectric current, that means suppose we increase the potential difference between the cathode and the anode plate, naturally the photoelectric current increases. On the other hand, let us say we interchange the voltage, in the sense the cathode is connected to positive and the anode is connected to negative. If that is the case, then you don't know, even for a small negative voltage given to the anode or positive voltage given to the cathode, the number of electrons will be emitted, and highly energetic electrons would be able to reach the anode, and thus we get current, and that current is feeble. So if we keep on increasing at one particular stage, the number of electrons emitted by the cathode will be there because of the incident radiation. But these electrons will not be able to reach the anode because the anode is at negative potential. They are not attracted by the anode. On the other hand, cathode, surrounding the cathode or around the cathode, those electrons will be accumulated. So at one particular voltage, negative voltage given retarding potential, this is what you see in the last sentence. If negative retarding potential is given to the anode plate and positive to the cathode plate, the electrons are repelled and only the most energy. That means at some stage there will be no photoelectric current, and that we call it as the stopping potential or stopping voltage. And these are the graphs. So the graph shows that variation of photocurrent with potential for different intensity of radiation. That means frequency constant and the voltage is also constant. Then intensity will vary, means the photoelectric current increases, I2 greater than I1. And in the other graph, effect of frequency of incident radiation on stopping potential, different stopping potential we have for different frequency, like nu3 greater than nu2 greater than nu1, but saturation current remains the same. This is what you can see. And the time is and finally I give you this equation, that half mv square is equal to h nu minus h nu naught, and this equation is what we call it as the photoelectric equation. And this photoelectric equation, half mv square is equal to h nu minus h nu naught. We can even write like this because k is equal to k means half mv square. You can also write it as ev naught, and that is nothing but h nu is equal to h nu h minus h nu. We can even write in a slightly different way. That means I will have no time to discuss all these things. And in fact, the I just made a mention about only electromagnetic theory could not explain the photoelectric effect, black body radiation, Compton effect. In fact, it was uh, what is that? Max Planck, who introduced the quantum theory. Based on quantum theory, Einstein explained the phenomenon of photoelectric effect, for which he got the Nobel Prize in the year 1921. And Millikan conducted the Millikan oils experiment. We say that he conducted the experiment for verifying. That was in the year 1920. Sorry, what is that? 1816. Sorry, 1916. In fact, Millikan was trying to find out fault with the Einstein's photoelectric equation, but when he did the experiment, he came to the conclusion what Einstein has done is correct. So I think it is time up. I may have to close down, and I should give you some time for you to ask questions. Later on, if in case if there is any possibility, I will continue from this onwards, and I will also talk about what is about the duality in nature again, and then further Davis and Germer experiment, because all those things are there in your syllabus. Especially to talk about the Davis and Germer experiment, G.P. Thompson experiment, it needs another 1 hour, because this is supposed to be a very big chapter, and naturally it will not be able to complete it in 1 hour. So ಇಷ್ಟೆಲ್ಲ ಕೇಳಿಸ್ಕೊಂಡಿದ್ದೀರಾ? ಮತ್ತೆ ನಿಮ್ಗಿನ್ನೇನಾದ್ರೂ ಮಧ್ಯದಲ್ಲಿ ಡೌಟ್ ಇದ್ರೆ ಈಗ ನೀವು ಕೇಳ್ಬೋದು. ಸೊ ಅದಕ್ಕೆ ಸಿದ್ದೇಗೌಡರು ಮತ್ತೆ ಉಳಿದವ್ರಿಗೆ ನಿಲ್ಲಿಸ್ಲಾ ಈಗ? ಅಥವಾ ಕಂಟಿನ್ಯೂ ಮಾಡ್ಲಾ, ಹೇಳ್ತೀರಾ?
ಸರ್ ನೆಕ್ಸ್ಟ್ ಟೈಮ್ ನಿಮ್ಗೆ
ಹಾ.
ನಾನು ಇದು ಕಂಟಿನ್ಯೂ ಮಾಡೋದಾದ್ರೆ ನಾನು ನಿಮ್ಗೊಂದು ಟೈಮ್ ಕೊಡ್ತೀನಿ ಸರ್. ದಯವಿಟ್ಟು ನಾನು ಸರ್ ಜೊತೆ ಮಾತಾಡಿ.
ಆಯ್ತು ಆಯ್ತು. ಯಾಕೆಂದ್ರೆ ಇಲ್ಲಿಂದ ಮುಂದಕ್ಕೂ ಸ್ವಲ್ಪ ಇಂಪಾರ್ಟೆಂಟ್ ರಿಸಲ್ಟ್ಸ್ ಇದೆ.
ಎಸ್ ಸರ್, ಶೋರ್ ಶೋರ್
ಆ,
ಶೋರ್
ಆ,
ಸರ್.
ಇದಕ್ಕೆ
ಡಿಸ್ಕಸ್ ಮಾಡಿ
ಯಾಕಂದ್ರೆ ಇದು ಇವ್ನ್ ಮಿಲಿಕನ್ ಮಾಡಿದ್ದು, ಆಮೇಲೆ ಐನ್ಸ್ಟೈನ್, ಈಗೆಲ್ಲ ಸುಮ್ನೆ ಹೇಳ್ಬಿಟ್ಟೆ ಅಷ್ಟೇ. ಆ ಹುಡುಗರುಗಳಿಗೆ ಸ್ಟೂಡೆಂಟ್ಸ್ ಅರ್ಥವಾಗಿದೆಯಲ್ಲೋ
ಇಲ್ಲ
ಗೊತ್ತಿಲ್ಲ.
ಇಲ್ಲ, ಬೇಡಿ ಸರ್.
ಹಾ?
ನಂದು ಅವರ ಟೈಮ್ ತಗೊಂಡು ಒಂದು ಕ್ಲಾಸ್ ನಾನು ಹೇಳ್ತೀನಿ ಸರ್, ಅರೇಂಜ್ ಮಾಡ್ಕೊಡ್ತೀನಿ ಸರ್.
ಆಯ್ತು ಆಯ್ತು, ಖಂಡಿತವಾಗೂನು ಫುಲ್ಲು ಒಂದ್ ಸ್ವಲ್ಪ ಕವರ್ ಮಾಡಿದ್ರೆ ಅವ್ರಿಗೂ ಒಂದು
Okay, sir.
ಐಡಿಯಾ ಬರ್ಬೋದು. ಆಮೇಲೆ ಇನ್ನೂ ಒಂದಷ್ಟು CET ಕ್ವಶನ್ಸು ಮಧ್ಯೆ ಹೇಳ್ತೀನಿ. ಈಗಲೂ
Okay, sir.
ಹೇಳಿದೀನಿ ಪ್ರಾಬ್ಲಮ್ ಹೇಗೆ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡೋದು, ಮತ್ತೆ ಯಾವ ತರದ್ದು CET ಕ್ವಶನ್ ಬರ್ಬೋದು ಅಂತ ತಾವು ಹೇಳಿದ್ದ ಹಾಗೆ ಹೇಳಿದೀನಿ. ಅದ್ರಲ್ಲಿ
Okay,
ಎಷ್ಟು ಅವ್ರಿಗೆ ಅರ್ಥವಾಗಿದೆಯೋ ಗೊತ್ತಿಲ್ಲ. ಬೇಕಾದ್ರೆ ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಇದನ್ನ ಕಂಪ್ಲೀಟ್ ಮಾಡ್ಬಿಟ್ಟು ಒಂದ್ 5-6 ಕ್ವಶನ್ CET ಕ್ವಶನ್ ತಗೊಂಡು ಹೇಗೆ ಸಾಲ್ವ್ ಮಾಡೋದು ಅಂತಾನು ಹೇಳ್ತೀನಿ.
ಸರ್.
ಖಂಡಿತವಾಗೂ.
ವಿದ್ಯಾರ್ಥಿಗಳೇ, ತಮ್ಗೇನಾದ್ರೂ ಈ ಹೊತ್ತಿನ ಒಂದು ಟಾಪಿಕ್ ಮೇಲೆ ಡೌಟ್ಸ್ ಆಗ್ಲಿ, ಏನಾದ್ರು ಕ್ವಶನ್ಸ್ ಕೇಳುವಂತ ಇಂಟೆನ್ಷನ್ ಇದ್ರೆ ದಯವಿಟ್ಟು ಸರ್ ನೇರವಾಗಿ ಜೊತೆಲಿದ್ದಾರೆ, ಒನ್ ಟು ಒನ್, ಯಾವುದೇ ಸಂಕೋಚ ಇಲ್ದೇನೆ ತಾವು ಕೇಳಬಹುದು.
ಕೊನೆಯಲ್ಲಿ ಸ್ವಲ್ಪ ಸುಮ್ಮನೆ ಹೇಳ್ಬಿಟ್ಟಿದೀನಿ, ಅಷ್ಟೆಲ್ಲ ಅವ್ರಿಗೆ ಡೀಟೇಲ್ ಆಗಿ ಹೇಳಕ್ ಹೋಗಿಲ್ಲ.
ಇರ್ಲಿ ಸರ್, ನೆಕ್ಸ್ಟ್ ಫ್ಯೂಚರ್ ಡೇಸ್ ಒಂದ್ ದಿವಸ ಒಂದು ಅನದರ್ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಕಂಟಿನ್ಯೂ ಮಾಡೋದು ಸರ್.
ಹೌದೌದು, ಖಂಡಿತ. ನಾನು ಇಲ್ಲಿಂದ ಮುಂದಕ್ಕೆ ಕಂಟಿನ್ಯೂ ಮಾಡ್ಕೋಬಹುದು.
ಓಕೆ ಸರ್.
ವಿದ್ಯಾರ್ಥಿಗಳೇ, ತಮ್ಗೆ ಇನ್ನೇನಾದ್ರೂ ಡೌಟ್ ಇದ್ರೆ, ಕ್ಲಾರಿಫಿಕೇಶನ್ ಬೇಕಾಗಿದ್ರೆ, ಅಥವಾ ಕೆಲವು ಪ್ರಾಬ್ಲಮ್ಸ್ ಹೇಗ್ ಮಾಡೋದು, ಈಗ ಇನ್ನೊಂದು ನಾನು ಈ ಫೋಟೋ ಎಲೆಕ್ಟ್ರಿಕ್ ಎಫೆಕ್ಟ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಬೇಕಾದ್ರೆ ನಿಮಗೆ ರ್ಯಾಲೆ ಜೀನ್ಸ್ ಲಾ ಅನ್ನೋದು ಬೇಕು. ಈಗ ಪ್ಲಾಂಕ್ಸ್ ಕ್ವಾಂಟಮ್ ಥಿಯರಿನ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಬೇಕು ಅಂದ್ರೆ ರ್ಯಾಲೆ ಜೀನ್ಸ್ ಲಾ ಏನ್ ಹೇಳ್ತು, ಹಾಗೆ ವೀನ್ಸ್ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಲಾ ಅಂದ್ರೆ ಏನು, ವೀನ್ಸ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಲಾ ಯಾವನು ಟಚ್ ಮಾಡಕ್ ಹೋಗ್ಲಿಲ್ಲ. ಯಾಕಂದ್ರೆ ಅವನ್ನ ಎಲ್ಲ ಹೇಳಕ್ ಹೋದ್ರೆ ತುಂಬಾ ಟೈಮ್ ತಗೊಳುತ್ತೆ, ಹಾಗಾಗಿ ಅವನ್ನ ಹೇಳಕ್ ಹೋಗ್ಲಿಲ್ಲ. ಅಂದ್ರೆ ಐನ್ಸ್ಟೈನ್ ರ್ಯಾಲೆ ಜೀನ್ಸ್ ಲಾ ಹಾಗೆ ವೀನ್ಸ್ ಲಾ ಇವೆಲ್ಲನೂ ತುಂಬಾ ಇಂಪಾರ್ಟೆಂಟು. ಹಾಗಾಗಿನೇ ಪ್ಲಾಂಕ್ಸ್ ಕ್ವಾಂಟಮ್ ಥಿಯರಿ ಯಾಕೆ ಹುಟ್ಕೋತು, ಆ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ಥಿಯರಿ, ಫೋಟೋ ಎಲೆಕ್ಟ್ರಿಕ್ ಎಫೆಕ್ಟ್ ನ, ಕಾಂಪ್ಟನ್ ಎಫೆಕ್ಟ್ ನ, ಅಟಾಮಿಕ್ ಸ್ಪೆಕ್ಟ್ರನ ಸರಿಗೆ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಕ್ ಆಗ್ಲಿಲ್ಲ. ಅದರಲ್ಲಿ ಅದರದೇ ಆದಂತ ಡ್ರಾಬ್ಯಾಕ್ ಇತ್ತು. ಅದಕ್ಕೋಸ್ಕರ ಪ್ಲಾಂಕ್ಸ್ ಕ್ವಾಂಟಮ್ ಥಿಯರಿನ ಮ್ಯಾಕ್ಸ್ ಪ್ಲಾಂಕ್ ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡಿದ್ದು.
ಸರ್, ನಿರ್ಮಲಾ ಎಲಿಗಾರ್ ಅವರು ಒಂದು ಕ್ವಶನ್ ಕೇಳಿದರೆ, ವಾಟ್ ಈಸ್ ದ ಡಿಫರೆನ್ಸ್ ಬಿಟ್ವೀನ್ ಎಕ್ಸ್-ರೇಸ್ ಅಂಡ್ ಗಾಮಾ ರೇಸ್ ಅಂತ ಕೇಳಿದ್ದಾರೆ ಸರ್. ವೈರೇಸ್ ಅಂತ ಕಾಣಿಸ್ತಾ ಇದೆ ನೋಡಿ, ಗಾಮಾ ರೇಸ್ ವೈರೇಸ್.
ಆಯ್ತು, ಹೇಳ್ತೀನಿ. ಎಕ್ಸ್-ರೇಸು ಲೋ ಎನರ್ಜಿ ಅಂತ ಹೇಳ್ತೀವಿ. ಲೋ ಎನರ್ಜಿ ಅಂದ್ರೆ ಈಗ ಎಕ್ಸ್-ರೇಸ್ಗೆ ಫ್ರೀಕ್ವೆನ್ಸಿ ಎಷ್ಟಿರ್ಬೋದು ಅಂದ್ರೆ 10⁻20 to 19 to 20 ಫ್ರೀಕ್ವೆನ್ಸಿ. ಹಾಗೆ ಗಾಮಾ ರೇಡಿಯೇಷನ್ಗೆ ಫ್ರೀಕ್ವೆನ್ಸಿ 10⁻22 ಇರುತ್ತೆ. ನೀವು ಏನಾದ್ರೂ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ಸ್ಪೆಕ್ಟ್ರಮ್ ನ ಎಡಗಡೆಯಿಂದ ಬಲಗಡೆಗೆ ಬರ್ಕೊಂಡ್ರೆ, ಎರಡು ಹೇಳ್ತೀನಿ. ಮೊದಲು ಗಾಮಾ ರೇಡಿಯೇಷನ್ ಬರಿತೀವಿ, ಅದರ ವೇವ್ ಲೆಂತ್ ಅನ್ನ 0.00001 ನ್ಯಾನೋಮೀಟರ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಅಥವಾ ಹೇಗೆ ಹೇಳ್ಬೋದು ಅಂದ್ರೆ 10⁻⁻12 ಹಾಕ್ಬೋದು, 10⁻⁻12 ಮೀಟರ್. ಅದೇ ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ ಬಂದ್ರೆ 10⁻⁻10 -11 ಆ ರೇಂಜ್ ಅಲ್ಲಿ ಬರುತ್ತೆ. ಫ್ರೀಕ್ವೆನ್ಸಿ ಜಾಸ್ತಿ ಇರೋದ್ರಿಂದ ಗಾಮಾ ರೇಡಿಯೇಷನ್ಗೆ ಎನರ್ಜಿ ಜಾಸ್ತಿ ಆಗುತ್ತೆ, ಹಾಗೆ ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ಗೆ ಎನರ್ಜಿ ಕಡಿಮೆ ಇರುತ್ತೆ. ಗಾಮಾ ರೇಡಿಯೇಷನ್ ನಾವು ಸಾಮಾನ್ಯವಾಗಿ ಹೈ ಎನರ್ಜಿ ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ ಅಂತೀವಿ. ಅದೇ ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ ಅನ್ನ ಬೇಕಾದ್ರೆ ಲೋ ಎನರ್ಜಿ ಗಾಮಾ ರೇಡಿಯೇಷನ್ ಅಂತಾನು ಕರಿಬಹುದು. ಹಾಗಾಗಿ ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ ಮತ್ತೆ ಗಾಮಾ ರೇಡಿಯೇಷನ್ ನಾನು ಆಗ್ಲೇ ಹೇಳಿದೆ. ಎಡಗಡೆಯಿಂದ ನಾವು ಶುರು ಮಾಡಿದ್ರೆ ಫಸ್ಟ್ ಗಾಮಾ ರೇಡಿಯೇಷನ್ ಬರುತ್ತೆ, ಆಮೇಲೆ ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ ಬರುತ್ತೆ. ಅದೇ ನೀವು ಎಡಗಡೆಯಿಂದ ಫಸ್ಟ್ ಶುರು ಮಾಡಿದ್ರೆ ಯಾವುದು ರೇಡಿಯೋ ವೇವ್ಸ್ ಬರುತ್ತೆ, ಕೊನೆಯಲ್ಲಿ ಗಾಮಾ ರೇಡಿಯೇಷನ್ ಬರುತ್ತೆ. ಐದರ್ ಯು ಕ್ಯಾನ್ ರೈಟ್ ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ಇನ್ಕ್ರೀಸಿಂಗ್ ವೇವ್ ಲೆಂತ್ ಆರ್ ಡಿಕ್ರೀಸಿಂಗ್ ವೇವ್ ಲೆಂತ್, ಹೇಗಾದ್ರೂ ಬರೀಬಹುದು. ಡಿಫರೆನ್ಸ್ ಏನು ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ ಅಂದ್ರೆ, ಗಾಮಾ ರೇಡಿಯೇಷನ್ ಹೈಲಿ ಎನರ್ಜೆಟಿಕ್, ಒಂದು ಪಕ್ಷ ಏನಾದ್ರೂ ನಾವೇನಾದ್ರೂ ಗಾಮಾ ರೇಡಿಯೇಷನ್ಗೆ ಎಕ್ಸ್ಪೋಸ್ ಆದ್ರೆ ನಮ್ಮ ಸ್ಕಿನ್ ಪ್ರಾಬ್ಲಮ್ಮು ಅಥವಾ ಏನ್ ಪ್ರಾಬ್ಲಮ್ ಬೇಕಾದ್ರೂ ಆಗ್ಬೋದು. ಹಾಗೆ ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ ಅಲ್ಲೂ ಆಗುತ್ತೆ. ಎಕ್ಸ್ ರೇಡಿಯೇಷನ್ಗಿಂತ ಗಾಮಾ ರೇಡಿಯೇಷನ್ ಅಲ್ಲಿ ಜಾಸ್ತಿ ಅಫೆಕ್ಟ್ ಆಗುತ್ತೆ. ಮತ್ತೆ ಇನ್ನೇನಾದ್ರೂ ಇದೆಯಾ?
ಮತ್ತೆ ಯಾವ್ದು ಕ್ವಶನ್ಸ್ ಇಲ್ಲ ಸರ್. ಲೇಟರ್ ಅವ್ರು ಏನಾದ್ರು ಕಳಿಸಿದ್ರೆ ನಾನು ನಿಮ್ಗೆ
ಹಾ
ಇಮೇಲ್ ಮುಖಾಂತರ ನಾನು ಕಳಿಸ್ಕೊಡ್ತೀನಿ ಸರ್.
ಖಂಡಿತ ಖಂಡಿತ.
ಸೊ ಎನಿವೆ ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು.
ಇವತ್ತಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ತಾವು ಕೊಟ್ಟಂತ ಉಪನ್ಯಾಸ ಮಕ್ಕಳಿಗೆ ಕನ್ನಡ ಮತ್ತು ಇಂಗ್ಲಿಷ್ ಎರಡರಲ್ಲೂ ಕೂಡ ಬಾರಿ ಸರಳವಾಗಿ ಅವರಿಗೆ ತಲುಪುವ ರೀತಿಯಲ್ಲಿ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮ ನಡೆಸ್ಕೊಟ್ಟಿದ್ದೀರಾ ಸರ್. ಸೊ ಬಿಹಾಫ್ ಆಫ್ KSTA ಅಂಡ್ ಮೈಸೆಲ್ಫ್ ಒನ್ಸ್ ಅಗೇನ್ ಐ ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಸರ್ ನಾನು ನಿಮ್ಮೆಲ್ರಿಗೂ ಧನ್ಯವಾದನ ತಿಳಿಸ್ತಾ ಇದ್ದೀನಿ. ಐ ಥ್ಯಾಂಕ್ ದಿ ಚೇರ್ಮನ್, CEO, ದೆನ್ ಆಲ್ ದಿ ಸ್ಟಾಫ್ ಮೆಂಬರ್ಸ್, ಬಿಕಾಸ್ KSTA ಸ್ಟಾಫ್ ಮೆಂಬರ್ಸ್ ಅಂದ್ರೆ ಒಂಥರ ನಮ್ಮ ಸ್ಟಾಫ್ ಮೆಂಬರ್ಸ್ ಇದ್ದಂಗೆ ಆಗೋಗಿದೆ. ಸೊ ನಿಮ್ಮೆಲ್ಲರಿಗೂ ನನ್ನ ಧನ್ಯವಾದಗಳನ್ನ ತಿಳಿಸ್ತೀನಿ. ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್.
ವೆಲ್ಕಮ್ ಸರ್.
ಓಕೆ.
ಅದೇ ರೀತಿ ನಮ್ಮ ಈ ಒಂದು ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾಶೋಧನೆ ಯೋಜನೆ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳು ದಿನನಿತ್ಯ ನಮಗೆ ಸಲಹೆ ಸೂಚನೆಗಳನ್ನ ಕೊಡುತ್ತಾ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನ ಭಾರಿ ವಿಜೃಂಭಣೆಯಿಂದ ನಡೀಲಿ ಅಂತ ಮಾಡ್ತಿದ್ದಾರೆ. ಬಟ್ ನಮ್ಮ ವಿದ್ಯಾರ್ಥಿಗಳು ಸೂಕ್ತವಾಗಿ ಸರಿಯಾಗಿ ಜಾಯಿನ್ ಆಗ್ತಾ ಇಲ್ಲ ಸರ್. ಅದೇ ಒಂದು ಭಾರಿ ತೊಂದರೆ ಆಗಿದೆ ನಮಗೆ.
ಹೌದಾ? ಈಗ ಚೆನ್ನಾಗಿ ಬರ್ತಾ ಇದೆ? ಸ್ವಲ್ಪ ಸ್ಟ್ರೆಂತ್ ಏನಾದ್ರು
ಬರ್ತಾ ಇದ್ರೆ ಸ್ಟ್ರೆಂತ್ ಬರ್ತಾ ಇದ್ರೆ, ಬಟ್ ನಮ್ಗೆ ಸೆಲೆಕ್ಟ್ ಆಗಿರ್ತಕ್ಕಂಥ 320 ವಿದ್ಯಾರ್ಥಿಗಳು ಸರ್ ಆಕ್ಚುಲಿ. ಅದರಲ್ಲಿ ಕೆಲವು ವಿದ್ಯಾರ್ಥಿಗಳು ಮಾತ್ರ ಹಾಜರಾಗ್ತಾ ಇದಾರೆ ಡೈಲಿ. ಮತ್ತೆ ಯೂಟ್ಯೂಬ್ ಅಲ್ಲೂ ಕೂಡ ಕೆಲವು ವಿದ್ಯಾರ್ಥಿಗಳು ಅಟೆಂಡ್ ಆಗ್ತಾ ಇದಾರೆ. ಸೊ ನಾನು ಪ್ರತಿನಿತ್ಯನೂ ಕೂಡ ಅವ್ರಿಗೆ ವಾಟ್ಸ್ಆಪ್ ಗ್ರೂಪ್ ಮತ್ತೆ ಇದ್ರಲ್ಲೆಲ್ಲ ಮೆಸೇಜ್ ಆಗ್ತಾ ಇದ್ದೀನಿ, ಮತ್ತೆ ನಾನು ಇಮೇಲ್ ಅಲ್ಲೂ ಕೂಡ ಕಳಿಸ್ತಾ ಇದ್ದೀನಿ. ಇದೇ ರೀತಿ ಪುನರಾವರ್ತನೆ ಆದ್ರೆ ಅವರು ಸ್ಕಾಲರ್ಶಿಪ್ ಅಮೌಂಟ್ ಕಳ್ಕೊತಾರೆ, ಮತ್ತೆ ಈ ಕ್ಲಾಸ್ ಕೂಡ ರದ್ದು ಮಾಡುವಂತ ಒಂದು ಸಂದರ್ಭ ಬರ್ಬೋದು ಅಂತ ಹೇಳಿದೀನಿ. ಹಾಗಾಗ್ಬಾರ್ದು ಅಂತ ಹೇಳಿ ನಾನು ವಿದ್ಯಾರ್ಥಿಗಳಲ್ಲಿ ಒಂದು ಮನವಿನೂ ಕೂಡ ಮಾಡಿ ನಿನ್ನೆ ಯಾರೊಬ್ರು ವಿದ್ಯಾರ್ಥಿನೂ ಕೂಡ ಒಂದು ಸ್ಟೇಟ್ಮೆಂಟ್ ಹಾಕಿದ್ದಾರೆ, ಈ ತರ ಆಗ್ಬಾರ್ದು.
ಒಂದೇ ಒಂದ್ ನಿಮಿಷ ತಗೊಳ್ತೀನಿ. ಬಹಳ ಹಿಂದೆ ಅದು ಸ್ಟುಡಿಯೋದಲ್ಲಿ ಮಾಡ್ತಿದ್ದು, ನಾವು ಆಕ್ಚುಲ್ ಆಗಿ CET ಇದಕ್ ಮಾಡ್ತಾ ಇದ್ದದ್ದು. ಅದನ್ನ ಸುಮಾರು 105 ಸೆಂಟರ್ ನಲ್ಲಿ ಮಾಡ್ತಾ ಇದ್ರು. ಆಗ ಯಾವ್ದೋ ಒಂದು ಇದಕ್ ಕೊಟ್ಟಿದ್ರು ಏಜೆನ್ಸಿಗೆ. ಅಂದ್ರೆ ಅವರು ನಮ್ಗೆ ಲ್ಯಾಪ್ಟಾಪ್ ಕೊಟ್ಟಿದ್ ಹೇಗಿರ್ತಿತ್ತು ಅಂದ್ರೆ, ಕ್ವಶನ್ಸ್ ಮೇಲೆ ಅದ್ರ ಕೆಳಗಡೆ ಬರೆದು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡೋ ಅಂತ ಅವಕಾಶ ಇರ್ತಿತ್ತು. ಆ ರೀತಿ ಏನಾದ್ರೂ ನಾವು ಚೇಂಜ್ ಮಾಡ್ಕೊಂಡ್ರೆ ನಮ್ಮ ವೇ ಆಫ್ ಟೀಚಿಂಗ್ ನ, ಅವ್ರಿಗೆ ಇನ್ನು ಸ್ವಲ್ಪ ಅರ್ಥ ಆಗ್ಬೋದೇನೋ. ಈಗ ಕೆಲವು ಸುಮ್ನೆ ನಾವು ಬಾಯಲ್ಲಿ ಹೇಳಿದಾಗ ಗೊತ್ತಾಗಲ್ಲ
ಸರ್. ಇಲ್ಲ ಅವ್ರಿಗೆ ಸಮಯದ ಒಂದು ಅಭಾವ, ಮತ್ತೆ ಆ ಟೈಮಲ್ಲಿ ಕ್ಲಾಸ್ ಗಳಿರುತ್ತೆ, ಮತ್ತೆ ಲೆಕ್ಚರರ್ಸ್ ಗಳು ಕೂಡ ಮೊಬೈಲ್ ತರಬಾರ್ದು ಅಂತ ಹೇಳೋದು, ಹಾಸ್ಟೆಲ್ ವಾರ್ಡನ್ಸ್ ಮೊಬೈಲ್ ತರಬಾರ್ದು ಅಂತ ಹೇಳೋದು. ನಾನು ಅದಕ್ಕೆ ಪ್ರತಿಯೊಂದಕ್ಕೆ ಹೇಳಿದೀನಿ ಸರ್, ನಮ್ಗೆ ಏನೇ ತೊಂದರೆ ಇದ್ರು ಪ್ಲೀಸ್ ಇಂಟಿಮೇಟ್, ನಮ್ಗೆ ಇಂಟಿಮೇಟ್ ಮಾಡಿ ಗ್ರೂಪ್ ಅಲ್ಲಿ ಹಾಕಿ ಈ ತರ ತೊಂದರೆ ಇದೆ ಅಂತ. ಅದನ್ನ ಸರಿಪಡಿಸಿ ನಿಮ್ಗೆ ಆ ವೇಳೆಗೆ ನೀವು ಕ್ಲಾಸ್ ಜಾಯ್ನ್ ಆಗುವಂಗೆ ನಾವ್ ಇಂಟಿಮೇಟ್ ಮಾಡ್ತೀವಿ ಅಂತ ಹೇಳಿದ್ರು ಕೂಡ ಮಕ್ಕಳು ಸರಿಯಾದ ಸ್ಥಿತಿ ಇಲ್ಲ. ನೋಡೋಣ, ನಾಳೆ ಡಿಸ್ಕಸ್ ಮಾಡಿ
ಖಂಡಿತ ಅದನ್ನ ಸಪರೇಟ್ ಆಗಿ ಡಿಸ್ಕಸ್ ಮಾಡೋಣ ಬೇಕಾದ್ರೆ. ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್ ಸರ್. ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು.
ಸೊ ಎಲ್ಲರಿಗೂ ಧನ್ಯವಾದಗಳು. ಸೊ ಇವತ್ತಿನ ಒಂದು ಈ ಕಾರ್ಯಕ್ರಮವನ್ನ ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಸೊ ಮತ್ತೆ ಸೋಮವಾರ ಯಾವುದೇ ತರಗತಿಗಳು ಇರುವುದಿಲ್ಲ. ಸೊ ಮಂಗಳವಾರದಿಂದ ಎಲ್ಲರೂ ಕೂಡ ಮತ್ತಷ್ಟು ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಜಾಯ್ನ್ ಆಗಿ ಅಂತ ಹೇಳ್ತಾ ಈ ಕಾರ್ಯಕ್ರಮನ ಮುಗಿಸ್ತಾ ಇದ್ದೀವಿ.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.